Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed about the choice of reference point for finding out the electric potential. Now today, we will discuss the importance of Poisson's equation and Laplace equation in electrostatics. Now in study of electrostatics, our motto is to find out electric field and electric potential in a region, right? Now you know that using Coulomb's law or Gauss's law, electric field can be determined when the charge distribution is specified. Now one can also this formula to find out electric field when the electric potential is specified throughout the region. But in practical problems in electrostatics, neither the charge distribution nor the potential is specified at some boundaries separating two mediums. These type of problems are known as electrostatic boundary value problems. Okay? And for these type of problems, electric field and electric potential are determined by using Poisson's equation or Laplace equation. And Laplace equation is a special case of Poisson's equation. Now that will be clear from the next slide. Okay. Now to construct Poisson's equation and Laplace equation, two important properties of electric field have to be considered. The first one is the differential form of Gauss's law, and the other one is the irrotational character of the electric field. So curl of electric field is 0, right? If any vector field is irrotational, the curl of that vector field will be 0. It also tells about the conservative property of the electric field that we have seen. Now, as the curl of gradient of any scalar field is 0, the electric field can be written like this. Electric field equal to minus gradient of potential, right? Now putting this form in this differential form of Gauss's law, we get del dot minus gradient of potential equal to rho by epsilon naught. So we get del square V equal to minus rho by epsilon naught, and this is called the Poisson's equation. Now in regions where there is no charge, we get Laplace equation which is of this form, that is del square V equal to 0. Now the significance of this equation is that there may be plenty of charge elsewhere, but we are confining our attention to places where there is no charge, and we want to find out the potential in that region. Okay. So here this is the del square operator and it is called the Laplacian operator. Okay. Now this Laplacian operator has different forms in different coordinate systems. In Cartesian coordinate, the form is like this: del square V del x2 plus del square V del y2 plus del square V del z2. Okay, this is the form in spherical coordinates where the components are r, theta and phi. And this is the form of del square operator in cylindrical coordinates where the components are s, phi and z. So here this s is the radius of that cylinder, right? So these are coming from this Cartesian coordinate to any other spherical or cylindrical coordinate. So we need the transformation equation that you know. Now you can see these are basically second order differential equation. So to find out the potential, we have to solve this second order differential equation considering boundary conditions. Now I will not discuss the detailed procedure of the solution. Rather, I will tell you the different methods to solve Poisson's equation and Laplace equation in a very general way. Now suppose if anyone do not have the knowledge of how to solve the second order partial differential equation, in that case for solution method of image has to be adopted. Okay. Now with the knowledge of how to solve partial differential equation, Green's function method has to be adopted to solve Poisson's equation. And to solve Laplace equation, we have to perform method of separation of variables considering appropriate boundary condition. So boundary condition is needed to solve this type of equations. Okay. Now solution of Laplace equation is actually unique. This is uniquely determined if the equation is specified on any boundary. Okay. So this is actually called the uniqueness theorem of Laplace equation. And the uniqueness theorem of Poisson's equation states that the equation has a unique gradient of solution. Okay. Now this means that there is a unique electric field derived from a potential function satisfying Poisson's equation under the boundary conditions. Now you are understanding that one should know what are boundary conditions to solve the Poisson's equation and Laplace equation, right? So this is the importance of Poisson's equation and Laplace equation. So using that we can find out the electric potential when we do not know the charge distribution. The charge distribution is not specified. Okay. So today I am ending here. In the next class we will discuss electrostatic boundary conditions and you will understand how to use that boundary conditions in differential equations. So that different boundary conditions we will discuss in the next class. Okay. Thank you.